Thanks for joining. Looks like we just kicked off, but there's a couple people trickling in. So we are on Facebook and Twitter and LinkedIn. Let's see. TikTok. I see TikTok going live. To Nova He, Talesman 1700. Thanks for joining. Doing some research today. And I was going to prep a little bit more, but on the one hand, I think it's good for y'all to kind of see me struggle bus and see how like a researcher actually deals with that. And then also, this comment was just so funny. I had to kick off the stream. So I have this question, right? I want to cite Stack Overflow answers in scientific publications. I share this question, so I'm glad it's already been asked, because I have been finding far more useful applied statistical information on Stack Overflow. I've been having wonderful conversations. I'll show you one of the conversations, but I've been having far more success there than going the traditional reading journal articles, which is just extremely time consuming. And often you end up with like not very good answers because these 5 papers will say X and these 6 papers will say Y. And so you've just read like 500 pages, mostly of irrelevant stuff, to look for the needle in the haystack, and the needle ends up being like indecisive, indecidable, ambiguous. And sometimes that's just how it be. But if you can get a straight up vote, like, answer A has 35 and answer B has 27, and if they're very clear and concise, it's really great, right? So the fact that this question has been asked and answered is really cool. Kind of got to blow my nose. I'm stuffy today. But the other thing is, this was just hilarious to me. This is an academic right here. I'm not familiar with this guy, but he's got a boatload of votes. He knows his stuff. And he said the GUIDs, the GUIDs, are fugly. I about died when I read this. So, anyway, I wanted to share that, and that's the reason for me kicking off early. Completed, see my revised accepted answer. So this is from like 10 years ago, right? So I don't know if it was actually implemented later. Was it? It looks like it was kind of implemented. We have official citation support, but this is enabled only on CS theory and math at the moment. Boo! Hopefully at the moment means 10 years ago, and since then it's been updated. Seems edited in 2017, so wonder if it's any better. Feature request, interesting. It has a feature request tag. Let me upload that. Oh, I already voted. Okay. And so let's now go to one of the cool questions I've been asking here on cross-validated cite. God bless. So I can cite revisions. So on Quora, we also see the same question. And a different but respectable answer on Quora. Quora says, so here's the top answer, I have done this. And it's like nobody upvoted it, so that's kind of questionable. If someone gives an answer but it's not upvoted, it's sus. So second answer, before my upvote, it had one upvote. So not like a strong signal, but better than nothing. And then I upvoted it because I think it's quite a good signal. Hey, Reisman, what's up? Thanks for joining. So Kelly says it's an unofficial reference. It's an unofficial reference. Now, I think that can be squabbled upon because it's like, if you go here, and if your question is answered by a Nobel Prize winner, I think you can consider that an official reference, because it's like, what is official reference? The guy's a Nobel Prize winner, right? That being said, there are a lot of like goofy answers from nobodies, so that would be unofficial. But if the person who answers you, like this guy Richard Hardy, I believe is university affiliated, and so that would make it, yeah. So PhD associate professor with work experience in finance, from Europe. Let's see if we can actually track him down. Associate professor Richard Hardy. right? So I would consider this a oh, I'm not sure that's the same guy, is it? Because he said Europe. Richard Hardy, I guess, is a fairly common name, isn't it? Yeah. So if you're really sus, I guess fine. Like look up the guy. I guess it would be better if you can track down the guy and like prove like, are you actually a PhD? Hmm. Yeah. So I get that it's not bulletproof. I get that, but I think it's like still pretty good, especially when the answer itself is good. And okay, maybe 7 votes. Yeah. So stuff like this should be clarified. Um, like how many votes makes it like a quote unquote strong answer. But I think at a certain point you can actually demonstrate like community uh, community consensus if there's just like a ton of votes on one. Okay, so let me give you the background on this specific question and answer back and forth related to my current paper. So my current paper, I'm really interested in feature identification, factor identification, variable selection. Those are all synonyms. I get that it's confusing that we use a bunch of different terms for the same thing. And then many people, not myself included, would have you believe that this is a different topic from model selection or model identification or model optimization. So I think it depends on the use case, but my use case is hypothesis testing at the factor relationship level with the gender factor specifically. I'm testing the importance of the gender factor. And so I would say there are some different definitions of a good model. And one definition of a good model is that it contains true factors rather than spurious variables, random variables, and so forth, that it contains true relations. So how do we identify a true relation? Well, one way you can do that is with the p-value. And so the old school way to do this is look for like a p-value that has like under 0.1 or under 0.05 or under 0.01, etc. And you would have like significance levels that refer to these various p-values. That's basically old. But I don't think that means we need to throw out p-value altogether. There are some people these days that just throw out p-value altogether. And I think that's dangerous due to included variable bias. Let's say I have a variable with a p of 0.9. What that means is that the probability of not beta is greater than the probability of beta by a factor of 9, because you have 0.9 on the beta. You have 0.9 on the not beta and 0.1 on the beta. So it's like 9 times more likely that the true coefficient is outside of the confidence interval. So it means your estimate is probably wrong. And when you have an incorrect estimate, you're subject to included variable bias. We talk a lot about omitted variable bias, and obviously that's a problem, but I think it's a mistake to ignore included variable bias, where an included variable will steal credit from another independent variable, and it will render other independent variable estimates incorrect. So for me, I care about the gender estimate here. So let's say that I have a spurious independent variable and it steals some credit from gender. Now gender doesn't look significant, right? Or maybe it steals so much from gender that gender now does look significant in the opposite direction, like it flipped the sign. So this is really dangerous. So basically, I want to see a p-value under 0.5. So if you're under 0.5, then the probability of beta exceeds the probability of not beta. Does that make sense? So that is an expected true effect. And I don't want like I don't need you to have a .01 or a .1 or a .05, like really, really strong factor relation. I don't need that. But here's what I do want is I want it to be under .5, preferably significantly under .5. So if we go with the old school like ideas of importance and significance, a heuristic is the 10% rule. And so you would say like 10% of .5 would make it under .45, or maybe you would just do a flat 10%, so .4. So if someone's giving me a peer review and they're saying, hey, like .49 is too weak for me, I'll be like, fine. But if they're like, hey, .39 is too weak for me, I'm like, you need to give me a reason now. You need to give me a reason why now. I could see you going down like under .5, even like .44. But if we're significantly more likely, right, not only are we under .5, we're significantly and importantly under .5. At that point, I feel like I have justification for inclusion, and there's omitted variable bias risk if I don't include it. So it's kind of like you need to include it. Anyway, those are ways to select factors or features or variables. They're not, so for me, a true model includes true effects. It's not missing effects, and it doesn't have any spurious effects, right? It's like the correct effects are there. And so that's how I would identify an optimal model. That's not the normal way statisticians identify an optimal model. There's a bunch of ways that people do this. So one is the use case of prediction. They say we don't even care about the p-values, we just care about the overall model performance in a predictive setting. So they might do like cross-validation and things like this. There's like optimal subset selection and backwards and forwards eliminate, or like backwards elimination and forwards addition of features. So stepwise. What else? Lasso. Lasso is a big one, and I think we'll be doing lasso today. But if you do a, so let's say you do a lasso. There's a tuning parameter. It's the lambda. So you have to tune it. And how do you tune it? In my view, it's fairly arbitrary. So in the last statement here, this person said that's kind of confused because Ben didn't say it was arbitrary. I said it was arbitrary. But anyway. Sorry, I'm getting distracted reading it. I want to give you all the backstory though. The backstory is like, how do you identify an optimal model? So if you have a lasso and if you tune it with a lambda, that lambda, you can tune it up and down, but you need to be optimizing against some metric. And so then and same is true for backwards elimination and forward selection and stepwise and best subset. So like all of these, or like ridge regression or elastic net. So those are the shrinkage class. So there's the shrinkage class, which includes like lasso, ridge regression, elastic net. There is the stepwise class, which includes, there's an actual technique called stepwise regression, which is, it's kind of confusing because sometimes people refer to the class and sometimes people refer to the actual stepwise technique. So the stepwise technique itself is sus, basically. But the stepwise class, under certain conditions, is less sus. Specifically, forward selection can be useful if you have far more variables than you do samples. And I actually do have more variables than I do samples. That's pretty much the only case that you'd want to use forward selection. Backwards elimination is useful for you. It is probably the best in the whole class because you can supervise and use prior knowledge to validate or guide the input variable pool. And so in my survey, that's definitely true. Like, even the questions on the survey are guided by prior knowledge and expert knowledge and theory. They're informed by theory. So for these reasons, backwards elimination would be really well suited in my case. It'd be extremely defensible in my case, except that I have too many variables. So with backwards elimination, you would start by putting all of your plausible variables into a model, and I would be using least squares, but you don't necessarily need to do that, but that's what I would be doing at first. And then eliminating the features, which is synonymous with the independent variables, one by one on some criteria. And we'd be using the p-value criteria, eliminating them one by one until you reach that question. Until what? So you have to be optimizing against some metric, whether you're using stepwise or shrinkage or best subset selection, which is like kind of its own class. Any of these. And then what is, RCECV. So with cross validation, still stepwise. Any of these, you still need a model selection criterion, is what we call it. And sometimes if you're like, I don't know which one, you'll just do like a bunch and you'll look for the consistent variable results. And I think that's a great idea. But the question is, like, if possible, can we identify a good criterion? So here, that brings us to this question. That's the background for this set of questions. So started out, I said, how to interpret increase to AIC and adjusted R squared. So what I was trying to do was use multiple. I was like, I'm not sure, this criteria, I'll just use both, right? So what's AIC? AIC, model selection. I can never say this right. How do you say that? Akaiki? Akiki? I used to live in a town called Akiki. This is Akiki, Maryland. So I don't think you say Akiki but then they're completely different languages. Like this guy is, what is he, Japanese, I think? And then this is like a Native American word. So I don't know. I'm going to call it AIC, right? So this is a metric which has some nice properties. And it also has some, let's say, suboptimal properties. Suboptimal, you always have to ask the question, like, compared to what? So answers include BIC, DIC, and WAIC. There's also AAIC, which I'm not really familiar with, but I've heard about it. Let's Google that together. Oh, MDL. What is this MDL? Or was it AICC? No, I'm not seeing it. What is this MDL though? Minimum description length. That's cool. I think I'm gonna have to hang on to this link. Close to the right. Let's go get our vector groups file. And another thing you can do is a principal components analysis. I can't do that because I have partial responses. So that's my reason that I can't do that, basically. Cool. So I would prefer simplicity is always something I'm going for. And a simple metric is adjusted R squared. And that's simple because everybody knows about it, and it's based on R squared, which is a basic elementary statistical metric. So R squared is like your model, how much of the variance in the observation is explained, the share of variance between 0 and 1. That's R squared. And the problem with R squared is that you can cheat it, basically. I can just add more and more variables, even if they're random variables and spurious variables, and the R squared will always increase. It will never decrease. So that's why we have the adjusted R squared. It introduces a penalty. And so what this has the effect of doing is if you have two models and they're the same model, but the second model is the same model plus a random variable, it will have a lower adjusted R squared, and higher is better. So the lower would be worse, it'd be eliminated, you would prefer the right model. Do you see? And so you can see how it combats random variables and spurious variables. Now, for some reason, so anyway, we'll get into it in a second, but basically for some reason, a lot of statisticians don't like using adjusted R squared, even though some do. And the logic is just completely just mysterious to me, because it's very straightforward to me how the thing is beneficial, and I think to most people. AIC has a nice mathematical proof in information theory, and basically it shows that you can do the same thing, that it will kind of like prefer the right model. Now it does this, I think both of these approaches, AIC and adjusted R squared, penalize in an arbitrary way. So if we look at the formula for adjusted R squared, so here's the formula. Let's see if we can get a prettier version of that formula. It's just going to stay ugly, isn't it? Okay. It's pretty ugly. But how you can think about this is there's a balance between the this is R squared. Where's the adjustment? I'm not seeing the adjustment there. That just looked like the formula for R squared to me. Let's see if we can have a different one. Should be like 1 minus, n minus k minus 1. Here you go. And there are different ways to express this that are mathematically equivalent, but this is the one I'm familiar with. The other one might have been right too, and I don't know. This is the one that looks good to me. So k is the number of variables. Say you keep increasing k. What are you going to do? You're going to reduce R squared. Do you see that? Keep increasing k. This denominator increases. So you have 1 over 1, 1 over 2, 1 over 3, 1 over 4. It's getting smaller and smaller. Ooh, hold on. That would not be what happens if k increases. If k increases, let's say your n is 1, which is ridiculous, but let's just say that. Then if your k is 1, you'll have a 0. If your k is 2, it goes negative. Let's say your n is 10 and your k is 2. Let's go with that. This bottom would be 8. K goes to 3. The bottom goes to 7. K goes to 4. Bottom goes to 6. And it's approaching 1. You can get 0 and you can get negative and weird things happen. Well, let's just think about the case where you're approaching 1. As you approach 1, the number will get bigger and bigger. But the whole thing is 1 minus this expression. So 1 minus this expression will be getting smaller and smaller. Okay. I don't think I explained that well, but fair enough. Let's move on. So you can see how as the number of independent variables approaches the number of samples, your R squared goes down. And there's this multiplying by n minus 1, so that the penalty is modified, so that the penalty is, I think this is right, more severe when you have less data. The penalty is more severe when you have less data. I think that's right. But if you think about it, like, why is it n minus 1? Like, why is it n minus k minus 1? It's kind of arbitrary. It's built to accomplish nothing more and nothing less than the end that I just said, which is to penalize spurious, like penalize having too many variables. And it accomplishes that, but there are an infinite number of ways to accomplish that. I could do n minus 2. I could do n minus 3. I could do n minus 2k minus 1. I could do n minus k squared minus 1. It's true that there's sort of a simplicity here, but that's just a sort of Occam's razor kind of heuristic. It's not like actually a proof, right? Occam's razor can produce false results. Newsflash. We can interpret this as sort of balancing variance of explanation and the number of factors and at a given sample size. Yes, you can make that interpretation, but why should they be evenly balanced? Why should we evenly weight variance of explanation and number of factors? Maybe we want to have factors that do a lot of explaining. So maybe we want the coefficient of k to be more than 1. Maybe we want the coefficient of k to be 2, as in the case of AIC. So in the case of AIC, the coefficient of k is 2. Like, why? It's kind of arbitrary. You could do the same thing with 4. It would still work. You could do the same thing with 1 or with 3. So that's why, to me, these both appear arbitrary. However, to say they're arbitrary is not to say they don't work. They both work. What it is to say is that it's not clear to me that one works better. So AIC has been called an efficient selector, and BIC has been called a consistent selector. But this notion of efficiency, I'm not sure exactly what it means. It's definitely not economic efficiency, because I can easily show that AIC will select an economically inefficient model in some cases. So I think it means something in information theory, but it's not very clear. I've done like hours of research on this, and it's not very clear to me. Nor is it clear to me what BIC being consistent means, but I haven't looked into it much. Let's look into that. I think it means it gives you the same factors every time, but I'm not sure. That would be, sometimes that's called stability. BIC is consistent in the sense that if the true model is among the candidates, the probability of selecting the true model approach is 1. For any model selection criterion to be consistent, it must behave suboptimally compared to AIC in terms of mean average squared error. Yeah, but optimizing against mean average squared error is such a flaw if you're trying to identify models that all have a p-value less than 0.5, because you could end up with like p-values of like 0.9 and stuff. So I really don't like this AIC. For my use case, because again, my use case is I want to know, I want the true coefficient of gender, and I don't want it to be biased by inclusion, and I don't want it to be biased by exclusion. And in my use case, I don't really care about the overall model performance. I care about my factor identification, because I'm doing hypothesis testing at the factor level. This is a different use case than the machine learning guys who are like, I don't really care what coefficients, what relations, all the factors, just throw the kitchen sink in there, as long as it's cross-validated and expected to perform in future sort of projections. That's their end goal, model performance. that's not my end goal here. Those are different end goals. I'm not 100% sure what we mean by posterior model probability. The revised or updated probability of an event occurring after taking into consideration new information. Yeah, that makes sense totally. That's Bayesian statistics. But is it a model measure? I guess it's a model measure. I care about the factor. I think I should just be looking at the p-value. Note here that the true model is defined as the smallest model containing f. I don't know what that means. If f is not in any of the candidate families, okay? When f is among the candidate families, there seems to be consensus that for the former case, BIC should be preferred and AIC should be chosen for the latter. Is the true model finite dimensional? Ooh, that's an interesting question. Okay, well, this was fun. So I'm gonna keep this link on hand. One, I think they use true model differently than me. Two, I think my model has an infinite dimensional, my model is infinite dimensional. And I would expect that for most models. To me, it strikes me like rational versus irrational numbers. The irrationals are just like infinitely more frequent. Okay, so let's close that. Yeah, so anyway, adjusted model selection, basically, this guy asks, like, is there any justification? And I'm like, okay, here's 4 justifications. I haven't gotten any upvotes, though. So why do I think adjusted R-square, like, what are the optimality properties? One is overfit mitigation. We've talked about, so, like, what is overfit? Overfit is, we can say that the inclusion of spurious or random variables is a case of overfit. Another definition of overfit is that you are explaining the error in a sample rather than the relation of interest in a sample. Another definition of overfit is that your model will have low predictive validity in a new data set. So those are all different ways of looking at the same thing, overfit. Simplicity and parsimony. I think we've shown like adjusted R-squared favors fewer factors, right? Shared understanding. I think more people understand R squared and adjusted R squared than understand AIC, BIC, DIC, WAIC, and the other alternatives. Semi-efficient factor identification. This is the property that adjusted R squared has, where say that a true relation is a relation that has a p-value of less than 0.5, which is to say the probability of beta is greater than the probability of not beta, which is to say it's probably true. It's not like certainly, but it's like it's probably true. In an objective sense, not in this prior like normative p-value 0.1.05 like normative academic consensus sense. This is actually an objective logical rule that if your p-value is under 0.5, that it is probably true in an objective sense, holding constant things like measurement error and like things outside of the statistical calculation itself. Then in that case, in every data set that I've worked, I haven't done a mathematical proof of this, but I can do an empirical proof. In every data set that I've worked, if the p-value of a factor is under, certainly under 0.5, but even under like 0.4, depending on the data set, I've seen it go like kind of like 0.28 to 0.35 range, but I've never seen like over 0.4. You're heading out? Have fun. If your p-value is under like 0.4, if you include it, the adjusted R squared will increase. And so in that sense, it's semi-efficient because it selects factors that are true. It selects factors with a p-value of under 0.5. Let's see if I can just Google that and find that real quick. Oh, there's like brownie or something on my bottle there. And I can say that the sample sizes that I've worked with range from like, you know, a couple dozen to a few thousand. So yeah, so it's really an empirical proof, not a mathematical proof. But I think it holds over a wide range of data, if not all data. There's no established association between p-value and R squared. Yeah, but adjusted R squared. R squared value is high. However, the p-value for all my independent variable is over 0.05. How could this happen? This question is only confusing to you if you've been taught like way outdated stats. Yeah, none of these are dealing with adjusted R squared. Okay. Anyway, let's close that. So this is interesting. Oh, that's interesting. And see, this is AICC. I don't know the difference between AIC and this AICC. So it seems like I shouldn't be using AIC anyway, because I have more independent variables than samples. So anyway, I'm thinking to do lasso. I'm going to use adjusted R squared backwards elimination. I'm going to fight about it. But I'll do like multiple analyses. Let's upvote this guy. And then maybe I'll do the AICC as well. DIC, WAIC, they look cool to me. So yeah, so the weird thing happened is I include the industry variable. If I include the industry variable in my model, adjusted R squared goes up, and AIC also goes up. AIC going up is a bad thing. So I get an inconsistent and ambiguous result on model quality about whether including industry is good or not. Now I know from prior knowledge that industry matters. So I'm going to go ahead and do it. Let's see. I don't think I mentioned the prior knowledge thing. But yeah, so I know from prior knowledge that industry matters. So I feel like I really do have an empirical proof here. Empirical evidence, anyway. Empirical evidence that adjusted R squared is sometimes preferred to AIC. I think that's a fair way to say it. Okay, cool. So in my methodology, let's go to the methodology. My empirical argument that sometimes, including in my use case, AR2 over AIC for model selection. AR2 selects um, okay. So yeah, basically I'm like, hey, how do I interpret this? Like, no one knows. They're like, oh, that's weird. They're like, why are you using adjusted R squared? You should just use AIC. I'm like, I think I have good reasons not to use AIC. And then like they're not upvoting or downvoting. It's just stuck on 0. They're saying a lot of things, but like, what do you mean by factor relations? Anyway, I'm still looking for any optimality justification for R squared adjust. The arguments you have provided are not quite what I'm looking for. So yeah, yeah. This person has like a different concept of optimality justification. So I think I've justified it, but I think they want like an information theory proof, which in my book, that's not justified, because if you have if you have a model that is optimized for some information theoretic reason, but it's like not, it's not economically optimized, then you have a bad model. Okay, let me actually write that down. That's going to be important. So I think I'm going to end up citing this. So yeah, that's kind of circling all the way back. I want to cite this conversation I've been having. Can I do that? Well, I'm dumb enough that it took me till now to see the cite button, but the answer is like, yeah. Cool. And so this thing, it was like asking my question, and they made a good point, which is like you actually need to care about the revision too. But I think the cite button does that, so I think we're good. Yeah, I mean, some journals might reject it, but I think some will allow it because there are scholars even saying that they've already done it. AIC has been called an efficient selection criterion, but this has an information theoretic meaning rather than an economic theoretic meaning. It can be easily shown that a model with AIC informatic inefficiency is efficient under economic analysis. Further, AIC can be shown to overfit even on information theoretic grounds. Proofs of AIC's efficiency use an unintuitive definition of a true model. For me, I consider a true model, oh no, that would be BIC, where they're proving the true model thing with BIC. BIC is supposed to select a true model, and AIC makes no such claim, but optimizes on error minimization instead. I'm interested. There seems to be a consensus. Let's talk about this consensus. It's like, yeah. a discussion on selection criteria. AIC, VIC, AICC, DIC, WAC, MDL, PCA. What else do we have? Versus stepwise. That's about it, right? Cool. Okay, so I think this is going to end up possibly needing to be a completely different paper. Cool. Because this is really not the focus of the paper. Like, the point of the paper is not to make a theoretical contribution to statistics. Okay, so let's build this familiarity count. I have some variables where it's like, are you familiar with this school? It's like yes or no, kind of binary. And I want to collect them so that if they're familiar with like all the schools, it's like 5. And some of them, it's like 3 or 4, etc. So they're not numeric is the problem. They're strings. So S for S, and if I don't know if they're going to be considered empty or if they're going to be considered like empty strings. So maybe I can do if they're empty strings. S for S in favorability columns if S is an empty string. That will include it. Cool, so I feel good about citing that stuff. So here's a list comprehension. I want to do a list comprehension sum. A list comprehension produces a list that's just as long as its input. You'll need one of Python's other functional tools, specifically reduce, to fold into a single value. Okay. So I'm fine reducing. Function tool stop reduce lambda. Okay. Oh, go away. Come on, geese for geese. Leave me alone. Reduce lambda A, B, if A is greater than B, else, and here's the list. So this would be favorability columns is list this time. Yeah, so let's see if this will work. So I don't think it's going to work because this is like a data frame. Boo. So A and B. So here's a favorability column. So we'll say A if, else A plus 1. So we're going to increment it. Nope, then it would still need to start as a 0. We need to initialize that A somehow. So I need like an array of zeros. I could prepend this with an array of zeros, but this feels like the whole wrong direction because I'm using a data frame. So I'm going to comment that. So like pandas, or I don't know if it's pandas or, yeah, pandas has data frames, or if it's, what's the series? There's some data frame sum. You just like sum. The thing is, this is not going to work because they're not numeric. So what I want to do, where, could make it where. Data frame count not empty cells. See, everyone's done all this stuff already. It's great. To count the number of cells missing data in each row, you probably want something like this. Is null. Okay. So is null sum. You can do that, huh? Okay. I think that's going to work. Yeah. So this works. I think I can do this. So df apply, I'm very happy with. That is actually like the data frame way to do it. So I apply a lambda. So x is going to be, yeah, and then along the axis columns. Boop. I'm pretty sure that's the same. Axis 1 is also axis columns. Let's use no error, great. All right, so I actually commented my familiarity count thing there. I just wanted to test if I could change axis 1 to axis columns without mutating my wrangle data. So it did mutate my wrangle data, so let's go see. What changed? It says the first row also changed, but I'm not seeing where. Let's do a text diff. Find difference. Okay, it's saying the whole thing is different. That's not really helpful. Compare and merge. What? I have no idea what just happened. Okay. I was hoping it would tell me like the part that was different, right? Split. Unified. Let's try it again. Diff Checker Pro. Nope, bye. Okay. Count non-NA cells for each column or row. I think I can use this. Person 5, age 4, single 5. Cool. Because it ignored the NaN. What if it was empty? So what I want to do, I think I can use this. If it treats empty as NaN, we'll find out. So what is even the code difference here? Is serious axis columns. Okay, yeah. So I think is serious I was using the axis rows, and that's the difference. Let's go look. Is serious should be computed incorrectly now. That'll tell us. Is serious false? Well, that's a good one. See, because it's giving us the it's telling us that that is not serious, and we agree with that because they're all 10s. There's all 1s, false. So it's still getting them. 10, 10, 10, 10. I don't see what the issue is. It's computing them correctly. All right, let's do axis 1 again and see if the diff goes away. It's like still saying there's a diff. I'm not seeing. Where's the diff, man? 979 under a month. Why are you red and green? It's like everything's different you're saying, but I'm not seeing it. Oh, continuous. Okay. That's what it is. The label substring continuous there is changed. Yep. Close to the right. So yeah, these worldview things, I renamed them continuous like that. Okay, so I'm happy with that. And I like the semantic naming more. Okay, so familiarity count, lambda is null sum axis columns. The thing is, I don't want to look in all of those. I don't want to look in all of the. Okay, so this is good. I only want to look in certain columns. I think I can just do this. Let's see. S for S in, what would that be? Have you heard of familiarity? Yeah. Favorability, familiarity. So here's familiarity columns. Should be familiarity. Familiarity. Okay. So I want to make sure I get this familiarity columns correct. Yep. Okay. Data frame apply lambda to some columns. See, they do it like this. That's what I was trying to do, right? Okay, for a single column, better use a map. Okay, yeah, I hear you. But what if I want to do like 2 columns, 2, 3 columns? Using apply on the data frame, calling axis 1, right? Definition x, return x0 plus x1. Yeah, this is good. Oh, you can just dot column it like that. Thank you, 384, good job. So the issue remains because I don't want to manually specify those column names. Okay. I kind of think I need to break out a function at this point instead of doing a lambda. Because I want to do a for each column, and yeah. Okay. So we'll do df dot apply lambda x. I'm going to say lambda of column. Column is null, sum? No. What we want to do is we want to compute familiarity count, and we want to pass column and familiarity columns. Okay. And so this will be a function of column and familiarity columns. Okay, so for column and familiarity columns, we'll have a total equals 0, and then we will eventually return total. Why is it mad at the cool. So for column and familiarity columns, oh, it sounds like my baby daughter is like mad, so I might have to go get her in a minute. If column is not equal empty, all right, let's see if that works. I think this should be called row, shouldn't it? All right, cool. So no error. Love to see that. So we're going for the count over there. Familiarity count. It's always 6, which feels bad. So I think what it's doing is it's testing the, because that should be the maximum value. I think it's just testing the name, which, hey, the program's right. So what I want to do is test the value, not the name. Yeah, so I should do if curve value is not empty. Let's try it again. Super quick, love to see it. And we still got all the 6s. What's going on? What's going on? Let's print curve value. This is going to print like a load of stuff, but I still want to see it. Because we're getting NaN. Okay. How do I test is non? I forgot. I always forget this. I must have looked this up like 100 times. Okay, math dot is not a number. Okay. I have no problem importing math, but I already have NumPy on hand, so, well, I thought I did. Okay, so let's import math then. I think we can stop with printing so much stuff. Must be a real number, not a string. Let's see. Well, if it's just a string, I think I can test it like this, if that's actually true. Is that right? Let's go look at all that stuff it dumped and see. They're consistently lowercase nan, consistently. So I'll just do this. I don't want to see sixes everywhere this time. Come on. Yo, what are you doing? You trying to kill me? Familiarity count. What's going on? What's going on? What's going on? So we got all this stuff. Show me some truths. It's like always false, even when it was not, even when it was. Okay, so this is like a panda series. Is it a panda series or a numpy series? I always forget those. So anyway, I think I want to test pandas test non. So I think I need to do it like the pandas or I need to do it their way. The most basic level is null or not null. So they're using pandas or numpy. And this is what I'm seeing, right? Is null. So let's do it like this. Just all lowercase like that. String object has no attribute is null. Problem is that you're trying to call is null on the value rather than the series or data frame applies your function to each value. If you want to check that value is null, you have to use pd.isNot or pd.isNull. Okay? Cool. Let's test these. Oh, I got some trues in there this time. Now what if I do it is null instead? Okay, seems to work either way. So I'm going to go is null, and then we're going to check that in and test the other to make sure that we're getting consistency. Okay. All right, so that calculated. Cool. And then let's go check 504. We'll just manually check the top few. Familiarity. Thought it was 504, wasn't it? So this is counting the empties. Yep. Okay, so that's inverted. So let's flip it. Sorry. Can I just do that? I can't do that. If not, so instead of 504, I ought to get like 162. 162 on the right hand. Here we go. 162. All right, we're happy. So this looks good. Computed that thing. Don't need a math library. Okay, so familiarity columns is good. This is all good. I don't need all this stuff anymore. This is all good. Let's go to the other file, factor group 3. This is just a bunch of notes, that's fine. Right click, close to the right. So the feature here is compute familiarity count, stage all, control enter on Windows, command enter on Mac, push it. All right, and now what we want to do is validate that switching over to the int is nah does not alter my counts, because if it does, it's kind of goofed, right? All right, so I ran it, the wrangle file didn't change, so isNaw and isNull seem to be producing consistent estimates. So in that case, it appears that it doesn't matter which you use. So I'll go for the isNull because for me that's more intuitive. And so yeah, then I can delete that comment. This will be chore clean extraneous comment. Do not know what just happened. Stage and push that. And thanks for tuning in, y'all. I'm going to call it there. So, I guess let's run it real quick, right? So we got this count. Let's run it in a regression. So we'll go over to the factor groups, right? And the count is a thoughts on alt creds factor group. So there's familiarity count. Let's look at the survey. So here's the survey. Thoughts on alternative credentials is page 1. There's the variable of interest at the top. This is expected conventionality. This is favorability to online education. So we have expected conventionality, favor online ed. It seems out of order. It's out of page order, but I arranged them alphabetically. Here's duration. There's duration. You could call it expected duration, fine. And then here is the count. So that's all of them for page 1, right? So that's all the variables in the thoughts on alternative credentials factor group. So let's test that factor group. So this would be M, is it 10 or 11? Right. Analysis 3, tab, autocomplete, enter. So it's a matter about duration. Duration is not defined. Okay. Oh, I did call it expected duration. Okay. Cool. So, do we have at least like a dozen degrees of freedom? Yeah, cool. Pretty good. 7 R squared. AIC 291, meh. N is 99, like that. The adjusted R squared is solid, 4.3. Now the problem here is that expected conventionality is kind of like cheating and question begging. And it's not really instrumentable because you can go around and tell people, hey, this is the true duration of the alternative credential. And you're informing people, and you can tell people, hey, this is a learning provider. This is Coursera. This is Udacity. And you're like raising awareness. And you can tell favor online ed is another iffy one. So 2 of these are more instrumental than the others. Favor online ed is kind of independent. It's like whether you think remote learning is cool doesn't automatically indicate whether you think alternative credentials are cool. And it's something you can pick up from other data sets. Like other people are measuring not necessarily favorability to remote learning, but at least like the tendency to engage in it is like ticking up. There's measures on that. You'd expect those to correlate. This one though is kind of a weird one. It's intended to isolate the own effect from the norm's other effect. But it really reduces generalizability of the model. So let's drop that. And I think you're going to see the adjusted R squared drops by like at least 0.05. So I'm looking for 3.8. Whoa, balls. That's hype. It's the factor that I didn't like. Dropping it improves the model. That's pretty dope. So it went to 445. It actually went up and adjusted R squared. Is that right? So expected conventionality is totally spurious. That is wild. Familiarity count is also spurious. Let's do this. Let's get a marginal on there. Can I do that? See if it has a marginal effect. So it improves, and then you get the expected like attenuating effect, like opposite direction, linear, and marginal. But the p-value is just like up in the sky. So like these don't matter. I'm kind of blown away by that, but cool. All right, so we will call it there. I guess I'll re-record the metrics on this one now that I've done this. So that's still 7.7, and that's 4.2 instead of 4.3. Boop. Got 99 and 293 after rounding. Hey, thanks for tuning in, y'all. Have a good one.